Hi, today on Recitation Lecture Week 5, I will be covering three main topics. The first one is how to derive transfer function for translational mechanical systems. The second topic is how to derive transfer function and also solving the time domain problem for simple electrical systems comprising of RLC circuits. And the third topic is how to simplify a complex block diagram into a simple one. Okay, let's start with the first topic. So the basic components in translational mechanical systems are spring, damper, and mass. For spring, so suppose you have a spring with spring constant K. Then if you are pulling the spring to the right with force F, then the spring will give a reaction with force equal to Kx, where x is the displacement that is occurring on the spring, because this thing is connected to a wall. So let's say this is a wall and the wall is stationary, then the displacement is just simply x. For the damper is similar, but instead of the displacement, the force will come from the velocity. So d times dx over dt. And for mass, the force is equal to the mass multiplied by the acceleration of the point. So m times d squared x of t over dt squared, which is m times a of t. So a is this is acceleration, this is velocity, and let us just say that this is a displacement. Okay, now the first problem is we have this system, and the question is what is the transfer function between the position of the mass and the input of the force. So the constant of the damper is d, the mass is m, and the spring constant is k. So to get the transfer function, then we need to use Newton's law of motion. So when the system is at equilibrium or at steady state, then the sum of force should be equal to zero. Okay, so let us start solving the first equation. So the first equation is corresponding to the spring. So as we are pulling this point to the right with force Ft, then the spring will give equal force but in the other direction, right? So minus k multiplied by the displacement occurring by the spring. But here, if we are pulling F to the right, then the point Y will also move to the right, as well as the point X. So the displacement occurring on the spring is YT minus XT. Okay, so this is the first equation. The second equation, sorry, this is again the sum of force at equilibrium is 0. So this time we have the system, the mass and the damper. So as we are pulling this point to the right, then the spring also will move to the right, and the spring at this point is connected to the mass, and as the spring moves to the right, then also the mass will also move to the right, but the mass will react with uh, force on the opposite direction from the spring. So this is the force from the spring. It is similar to this, and the reaction comes from the mass and the damper. So m times the acceleration from this point, which is x of t, so d squared xt over dt squared, and minus the damper and the velocity d, here dx over dt. Okay, and then from the first equation and the second equation, we get ft. So we can replace k multiplied by y of t minus x of t to this equation. So we get m d squared xt over dt squared minus d dxt over dt. And we can use Laplace transform. So Laplace f of t is f of s is m. Then the Laplace transform of d squared xt over dt squared given zero initial condition is s squared and x of s. This should be plus. So this is plus dx over dt is s x of s. Then transfer function is x of s over f of s. So you get 1 over s squared m plus sd. Okay. Actually, I need to mention that when you are deriving transfer functions, then you have two assumptions. First, for transfer function, then we are assuming that the initial conditions are all zero. So when you are deriving transfer function, then always remember that you are assuming that zero initial conditions. And also you need to write the transfer function in a standard form. So you have s to the power n plus a s to the power n minus 1 up to, say, this a1 a n. Also on the numerator similarly, so you need to express in this form of polynomial. Okay, so for this you need to divide the numerator and denominator with 1 over m, so s squared plus s d over m. Okay, so this is the transfer function of the system. Next, I have another translational system. This time I put the spring over here, and we still have the damper. Both are connected to a mass m. The mass has wheels, and this is the floor. Again, we are pulling the mass with some force to the right, and let us define the center of the mass as x. So the reference point x. The damper has constant d, the spring has constant k. Again, we need to find transfer function t of s, which is x of s over f of s. Okay, so again, to derive the transfer function, then we need to use Newton's law of motion. The sum of force equals 0 at equilibrium. So we have f of t to the right direction, then the reaction is minus because the direction is to the left. So minus the mass, the acceleration d squared xt over dt squared, also from the spring, minus k xt, also from the damper d times the velocity equals 0. Okay, and then you need to apply Laplace transform. We have, assuming 0 initial condition, f of s minus s squared m x of s minus k x of s, and then minus s d x of s. So x of s over f of s is 1 over s squared m plus s d plus k. You need to multiply numerator and denominator with 1 over m. You get 1 over m s squared plus s d over m plus k over m. Okay, so that's the answer for this problem. Next, we will move on to the second topic, which is about electrical systems. Okay, second topic, we have a resistor with resistance R. So what's the relation between the voltage and the current? So V, we know that VR T is R times the current. Okay, and if we take the Laplace transform, then simply become VRS R times I R S. Okay, the second important component is inductor with inductance L. So we know that the voltage of inductor is the inductance times the time derivative of the currents. So L times di inductance over dt. Okay, if we take the Laplace transform of this, then we get VL of S is L times S, then IL of S, again assuming zero initial condition. For capacitor with capacitance C, then the capacitor current IC of T is C times the time derivative of the voltage over dt So the Laplace transform is ICS times SC over VC of S. Or equivalently, you can write it with VC of S is 1 over SC times IC of S. Okay, so we will be using these three equations to solve the problem. Okay, so I will sorry about that. So I will give you the first example to A. Now suppose that we have the following circuit. So we have a DC power source, we have inductor, we have capacitor and resistor. They are connected in series to a power source, say Vi. So input voltage, and here we want to compute what is the time domain solution of the voltage on the resistor VO, which is the output voltage. So you have R, this is C, this is L. Okay, so what is VOT? So in time domain, given VIT is 5 volts. Okay, so you can solve this using several ways. So if you remember your network theory class, then you should be able to solve this using differential equations, right? But here I will be showing you how to solve it using Laplace transform, because if you use Laplace transform, then um, it will be much quicker to solve it. Okay, so that's one application in using Laplace transform. Okay, now how to solve it? If the first thing that comes to mind is that you can use KCL or KVL, right? But here, since we have derived these equations for RLC, then we can use them. First, realize that from this equation, then you know that R is like a resistance, right? You have the voltage is equal to resistance times current. Okay, similarly with this, so let's say for general purpose that R is impedance. So the relation, so V over I is impedance Z. Okay, this is Z. So we can say that for inductor, then the impedance for inductor is CL is in Laplace domain is S times inductance L. Similarly for capacitor, then the inductance for capacitor C is 1 over SC, and inductance for resistor is just R. Okay, this way we can use our voltage division to find the voltage on the resistor, right? Okay, now we know that the voltage on the resistor, so V0 T over, so V0 T, okay, so V0 of T is something times the input voltage. So what is this something? This something is the impedance R, right? We have R. Okay, so let's directly use the equation in Laplace domain. We have phi of s, phi of s. So based on voltage division, then we know that the voltage here is R over the total impedance, right? Which is R plus SL plus 1 over SC. This is the circuit equation in Laplace domain. So we get the transfer function, right? Because the transfer function is the output voltage over the input voltage. So this is I. Then you can multiply the numerator and denominator with S, SR over SR plus S squared L plus 1 over C. Okay. Now for simplicity, assume that R equals 1 ohm, L equals 1, C equals 1 with respect to their units. Okay, so this is just for simplicity. We are assuming that R, L, C are all of 1. So we have S over S squared plus S plus 1. Now the question is, what is the output voltage in time domain? So we need to solve this equation. So we know that phi 0 of S equals to S over S squared plus S plus 1 times phi I of S. But we know that phi I t is 5 volts. So from here, we know that in Laplace domain, then phi I of S is 5 over S, right? So we have 5, sorry, this is not 5, this is S. S over S squared plus S plus 1 times 5 over S. We have S here, so they cancel. We have 5 over S squared plus S plus 1. Okay, since this is, don't forget your sign. So we just need to inverse Laplace transform of this term. Okay, so you can look at the Laplace table, and if you look closely, then the solution will be e to the power uh, 8. So we have a some constant there, b some constant, sine or cosine. So this one may be sine c times t. So this, like, if you look at the table, then you know that this will be likely the form of the solution e 0 of t. You just need to find these a b c. Okay, this is nothing but you can write s plus 1 half squared plus square root of 3 over 2 squared 5. Okay, you can confirm that this denominator is equal to this form, s squared plus s plus 1. Since we have 5, then uh, 5 is 5 times 1. 1 is 2 over 2. So you have 10 over 1 half s plus 1 half squared plus square root of 3 times 1 half squared. So in time domain, v0 of t is 10, and then e to the power minus 1 half t, and then sine c is square root of 3 over 2t for t greater than or equal to 0. Okay, so this is the time domain solution of the voltage on R. Okay, so you need to ask yourself, does the solution make sense? So we need to check if our solution is right. So let's do sanity check. Okay, let's see. So in DC circuit, assuming zero initial condition, then as time t goes to infinity, then inductor will act as just as a wire, right? So it doesn't have resistance for ideal inductor, so we can assume that L, like this will be a closed circuit, and a capacitor will be open circuit, right? So we can say that the voltage on the resistor as time goes to infinity, it will go to zero, right? Because so that makes sense, because this equation here, if you take the limit of this equation for t approaching infinity, then this term right here, this will be decaying to zero. So as time goes to infinity, then the voltage on the resistor will go to zero. So that's how you confirm that this equation makes sense. Okay, so that's for a series circuit. What about some parallel circuit? So 2b, for 2b, we have the following circuit. We have power source, again vi t, inductor L, but in parallel with, sorry, so the inductor is in series with a parallel of resistor R and capacitor C. Okay, the same question, what is the time domain solution given 5 volts constant power voltage source? We have 5 volt again, so what is the output voltage? Okay, so let's do some analysis here. So as t goes to infinity, then L will be a closed circuit, and C will be open circuit, right? So we still have like a closed loop here because C is in parallel with R. So as t goes to infinity, you will have a closed circuit. Okay, then um, we can think that the voltage at infinity is 5 volts, right? Okay, again, so we will do the circuit analysis in Laplace domain. Okay, so phi 0 of S, so the output voltage, something multiplied by the input voltage. Again, we will be using voltage division. So what is the impedance of this parallel circuit um, from the capacitor and the resistor? So is Z C parallel with R over the total impedance. So is ZL plus ZC parallel with R. But ZC parallel with R is a ZC times R over ZC plus R. So you should be remembering this equation for parallel circuit. ZC, that is ZC. ZC is 1 over SC. So R over SC, which is 1 over SC plus R. Okay, so let's substitute. You have, let's simplify it first. You can multiply it with SC, so you have R1 plus SRC. So this R over 1 plus SRC. This is ZL is SL plus R over 1 plus SRC. This is your transfer function. Multiply numerator denominator with 1 plus SRC. You have R, and then you have 1 plus SRC SL over R. Okay, so this is what? This is nothing but S squared RLC plus SL plus R. Now we again, for simplicity, let us assume that R equals 1, L equals 1, C equals 1. So all of them are 1, then transfer function is simply 1 over S squared plus S plus 1, right? Now with Vi is 5 volt, then Vi of S is 5 over S. So it gives you VO of S is 1 over S squared plus S plus 1, and the input voltage is 5 over S. Okay, so you have 5 over S squared plus S plus 1. So we just need to solve this equation from Laplace domain to time domain. So we need to use inverse Laplace transform, and to do that we need to use the partial fraction expansion. So let's do that. So A over S plus the denominator S squared plus S plus 1. The term here is B S plus 1. Sorry, B S plus C. So we need to find these constants A, B, C. I hope you still remember how to do that. Then, so let's cross multiply S squared plus S plus 1. This is AS squared plus AS plus A plus BS squared plus CS. S over S squared plus S plus 1. Then this one is A plus B S squared plus the coefficient with S, we have A plus C, S, and then A. Okay, comparing this with this one, then we have three equations. A plus B is 0, A plus C is 0, and A is 5. From here we know that b must be minus 5, c same minus 5. So we have v o of s is 5 over s minus 5. This is s plus 1, s squared plus s plus 1. Okay, so look over here. So it is similar to this, like in the previous problem. So the solution might be something like this. We will have another term, e a e b t cosine c t, something like that. So we just need to work on this fraction, 5 over s minus 5. We know that this is s plus 1 half squared plus square root of 3 over 2 squared. Still have s plus 1. Since we have 1 half over here, then 1 is what? 1 is 1 half plus 1 half, right? Okay, so this is 5 over s minus 5 s plus 1 half over s plus 1 half squared plus blah blah blah, the same 1 half s plus 1 half squared plus square root of 3 over 2 squared. Okay, so you can use the table directly to get v0 of t is what? Is 5 over s is 5. Okay, minus 5. So let's just write 5 in parentheses. So this is 1, and this is what? This must be cosine. So e to the power minus 1 half t cosine square root of 3 over 2 t, then minus e power 1 half t sine square root of 3 over 2 t for t greater than or equal to 0. So sanity check. Okay, so we have established that as t goes to infinity, then the voltage on the resistor will be equal to 5, right? And if we take the limit of this equation for t to infinity, then we will have v0 of t will be equal to 5. Okay, so that makes sense. So this equation is correct. To check final time, then we can also use the final value theorem. So v0 t or t equals to infinity is limit s to 0 s times v0 of s. So but when you are using final value theorem, then you have to be careful, because final value theorem can only be applied if your system is stable. Otherwise you cannot use it. It doesn't make sense. Okay, so you have to make sure that your system first is stable. Then after you confirm that your system is stable, then you can use final value theorem. Okay, so this is what? This is limit s approaching 0. Then you can, so you have this term right here, right? So 5 over, so 5s over s times s squared plus s plus 1. You have s, they cancel. You have 5 over s squared plus s plus 1, but you substitute s with 0, you have 5. So 5-fold. Okay, so if you implement this on the previous problem, you will get, so v0 t at t infinity is limit s approaching 0 s times v0 of s, which is, oh, so this term right here, so s times 5 over s squared plus s plus 1. But since s is approaching 0, then this is s 0. Okay, so that makes sense. Okay, so we are now finished with the second topic. So let us move on to the last topic, which is block diagram reduction. For block diagram reduction, I hope you already studied about block diagram. So for this time, I will be just giving you a problem. So consider this block diagram. You have summation. You have summation block input. So this block diagram is in Laplace domain. You have g1. G1 can be any transfer function, plus minus. This is g2. This is g3. You have h1, so that connects to this, and then this is the output y of s. So this should be capital Y, and you have another feedback with gain h2. This connects to this point here between g2 and g3. So we need to simplify this into a simpler block diagram. U of s is something, I don't know, let's say f of s. This is y of s. So what is f of s? So you need to simplify this, right? There are some approaches that you can use to simplify it. What comes to my mind is, well, what if we move this connection here to the right side? Okay, let's do that. That's the first approach, is to move this point, this connection point, to the right side here. So from this point before g3 to the point after g3, let's redraw it, plus plus. Okay, so we can put the plus sign inside this summation block. U of s, g1 plus minus, this is h1, still h2, y of s, this is g3, but we move it here, right? But this is not correct, because this point here is not multiplied by g3, so the signal that is being fed to h2, it's not multiplied by this gain g3. But if you move this point here to here, then this point is multiplied by g3. So to compensate it, you need to multiply with 1 over g3, right? Okay, The next simplification is that you can um, put these two blocks into one, because this is just g through g2 multiplied by g3, and these two blocks is h2 over g3. So you have this third simplified block, g1 plus minus h1. This is g2 g3 y of s, and this feedback block is h2 over g3, right? So this is for this the first. So we have to we have to feedback systems, right? This is the first feedback system, this is the second feedback system. So let us simplify these two feedback systems. Gain plus minus. So let us simplify the smaller feedback system first, g1. So this is what this is negative feedback. So you should know that if you have negative feedback, then it can be simplified into g2 g3 over 1 plus g2 g3 h1 y of s h2 over g3. Again, you can simplify it into one block. So this is the next block is so this thing is just g1 multiplied by this block, so you have g1 g2 g3 over 1 plus g2 g3 h1, and then the denominator is the feedback. This is positive feedback, so you have minus 1 minus g1 g2 g3 over 1 plus g2 g3 h1 multiplied by this block, so h2 over g3 g3 cancels, and then you can multiply the numerator and denominator with 1 plus g2 g3 h1. This simplify further into the final block, which is g1 g2 g3. 1 is this 1 plus g2 g3 h1 minus g1 g2 h2. Okay, so this is the final simplified block diagram. So hopefully I don't make any mistake. So if you find any mistake, then let me know, sending me emails. Also, if you have any other questions or something that is not clear, then you can always ask me question, send me emails. Okay, so that's the end of this recitation lecture for week 5, and I will see you next time. Bye.